The Dynamic Cosmological Coupling Model, Ahmed Mohammed. Introduction. In modern cosmology, we face a persistent mystery. When we observe galaxies, galaxy clusters, and the large-scale structure of the universe, we consistently find that gravity appears stronger than what visible matter alone can explain. Stars at the outer edges of galaxies move faster than expected. Galaxies bend light more strongly than their luminous mass would suggest. On cosmic scales, structures hold together in ways that seem to require far more matter than we can see. The standard explanation is dark matter, an invisible substance that outweighs normal matter and dominates the universe. But despite decades of searching, the physical nature of dark matter remains unknown. The Dynamic Cosmological Coupling Model proposes a different question. What if the problem is not missing matter, but limited observation? Core idea. In this model, matter does not disappear, transform, or lose its gravitational influence. Instead, matter can gradually lose its observational coupling. That means it remains physically present and gravitationally active, but becomes increasingly inaccessible to electromagnetic observation, to light. In other words, gravity continues to feel the matter, but our telescopes no longer see it. Cosmic darkness, in this view, is not a new substance. It is a dynamical observational state. Observational coupling. We introduce the idea of a coupling between matter and observation. When coupling is strong, matter is visible. When coupling weakens, matter becomes difficult or impossible to detect electromagnetically. This coupling is not random. It depends on the dynamical environment of the matter itself, especially its motion. As relative acceleration or rotational velocity increases, observational coupling decreases smoothly and continuously. There is no sudden disappearance, no sharp boundary, only a gradual fading from observational accessibility. Velocity-dependent decoupling. In galaxies, stars, and gas closer to the center, move relatively slowly. In these regions, observational coupling remains close to full strength, and matter is easily detected. Farther out, rotational velocities increase. As velocity rises beyond a characteristic threshold, coupling begins to decline. The faster the motion, the weaker the coupling. This single effect changes how much mass we think we see, without changing how much mass actually exists. True mass versus observed mass. What we usually call observed mass is simply the fraction of matter that remains coupled to electromagnetic observation. The true physical mass is larger. As coupling weakens, the gap between observed mass and true mass grows. Gravity responds to the true mass. Light responds only to the coupled fraction. This mismatch naturally produces the gravitational effects commonly attributed to dark matter. No additional particles are required. Galactic rotation curves. In standard physics, the flat rotation curves of spiral galaxies require large halos of invisible matter. In the Dynamic Cosmological Coupling Model, flat rotation curves emerge naturally. As rotational velocity increases in the outer regions of galaxies, observational coupling decreases. This reduction compensates for the declining visible mass. The result is a nearly constant rotational speed, exactly what we observe. What appears as a dark matter halo is, in this framework, an observational effect rather than a physical structure. Vertical time in layered observation. To describe this behavior, we introduce the concept of vertical time. Linear time governs motion and evolution within a single observational layer. Vertical time describes transitions between layers of coupling. Matter does not move backward in time, vanish, or fragment. It shifts vertically in coupling space. From our observational layer, it appears to fade or disappear, but physically it remains present. Reality becomes observationally stratified, not ontologically fragmented. Black holes reinterpreted. In extreme environments such as black holes, acceleration gradients become enormous. In these conditions, observational coupling collapses rapidly. The event horizon is not interpreted as the end of physical existence. It is a coupling horizon. Beyond it, matter becomes fully decoupled from electromagnetic observation while remaining gravitationally real. This reinterpretation preserves the causal structure of space-time and avoids the need for singular breakdowns of physics at the horizon. Gravitational lensing. Because gravity responds to total mass, not just visible mass, gravitational lensing remains fully consistent with observations. Light bending reflects the full baryonic mass distributed across different coupling layers. This explains why lensing maps often agree with dark matter models without requiring exotic matter. Observational predictions. The model predicts several observable signatures. Coupling should decrease smoothly with increasing rotational velocity. Dwarf galaxies with low characteristic velocities should show near-complete coupling. High-velocity galaxies should transition earlier into weakly coupled regimes. Gravitational lensing should track total mass rather than visible mass alone. The radial acceleration relation should reflect coupling behavior rather than modified gravity. These predictions are testable with existing and future data. Falsifiability. The model is not immune to rejection. It fails if coupling behaves erratically rather than smoothly. It fails if coupling exceeds physical bounds or becomes negative. It fails if the characteristic velocity scale varies arbitrarily without correlation to galaxy properties. Clear failure conditions are essential for scientific validity. Philosophical implication. The dynamic cosmological coupling model shifts the question from what is the universe made of to what can we observe and why. Darkness becomes a boundary of perception, not of existence. The universe may be richer than what light alone can reveal. Conclusion. In this framework, dark matter phenomena emerge naturally from velocity-dependent observational decoupling. Gravity remains unchanged. Matter remains baryonic. What changes is our access. The dynamic cosmological coupling model offers a coherent, testable alternative perspective on cosmic darkness, not as missing matter, but as hidden presence.